Point 2, estimate the cost. From this title, you can see we are going to do efficiency analysis. Here, the cost here means number of operations. Yeah. Because the larger this number of operations, the higher the cost. So that in general, we can call the cost function. The counting number, that function, we can also call it the cost function. Yeah. All right, so let's look at the problem. Yeah. All right, so our goal, find the number of operations. More specifically, 2 types of operations. Count the number of additions, and the number of multiplications. Yeah. All right, yeah. All right, in order to do that, yeah, because 2 parts, right? Yeah, 2 parts. Yeah, 2 parts. Here, because we didn't count the number of additions, right? Do we count the number of additions? We didn't count it in the previous. Yeah. So let's count that first, because that's pretty easy. Remember, we use the counting by reference technique. First, let me show you how to use it as our first example. All right, the first plus sign we associate with A1, 1-to-1 correspondence. The second plus sign we associate with A2, x squared. Yeah. Then the last plus sign we associate with A sub n. You see, 1-to-1 correspondence, right? Now, in order to count the number of plus signs, we just count the number of A's we use in this counting. That's easy, right? Yep. Number of A's, because A1, A2, consecutive subscripts until we get A sub n. Consecutive subscripts, we just use the subscript numbers from 1 through n. How many of them? Yeah. So it is simple. There are n. Then our conclusion, the number of additions, n. How about that? So this is the first time we use this technique, counting by reference, in this way. Okay. Later we will use it several times. All right. So next, this time we need to count the number of multiplications, because it is a little harder than counting the number of additions. Yeah. All right. In order to count the total number of multiplications, we need to count the number of multiplications in each term, ak times x to the kth power. If we can get this counting number, then we add up all the numbers corresponding to all the terms in this polynomial, we get the answer. So that's the idea. So let's do it. Yeah. All right. Yeah. Adding up, that's easy. Yeah. So let's do the counting for each term first. Yeah. So when we do the work, yes, this work, how to do it? Do you have some good idea? to solve this problem, another subproblem we need to solve for this particular computing problem. Do you have any idea? Yeah. So here, now I want to introduce you a special strategy that I mentioned it in part A. Remember part A? Yeah. The first video, 8.1. So look at that. 8.1, I mentioned strategy. Yeah, this one there. Yeah. Try simple examples. Try simple examples. Yeah. So look at the k equals 1 case. When k equals 1, a1 times x. How many multiplications you need to do in this, calculating this term? 1, right? Yeah. Try another simple example. How many multiplications do you need to do in calculating this term? 2, right? The coefficient times a squared, but to calculate a squared, you do 1 multiplication, x times x. So you get 2. All right? Yeah. In this way and so on. So when you do ak times x to the kth, so you can see it's very easy, you get k, right? Yeah. So the same number as the subscript number. When the subscript number equals 1, the number of multiplication number also 1. When the subscript number is 2, the number of multiplications you need is 2, and so on. So when the subscript equals k, the number of multiplications you need equals k. So that's the induction way we use here. Yeah. So we can get the answer. Yeah. For the typical term, the number of multiplications equals this k. Yeah. Then adding up, now we can do that part, adding up, that work. Yeah. Here I use a simple table here. Yeah. So you can see the top line, I list all the terms that require multiplications. Yeah. The bottom row, yeah, the non-corresponding number of multiplications for each term. Yeah. So you can see adding up 1 plus 2 all the way through n, that number by the formula 1/2 times n plus 1. Okay, so we find the total number of multiplications. Now, then think about, we have the total number of additions, so that's n. Yeah, we found before. Yeah. Now this number of multiplications. At the end, we want to combine them. Remember our 2 assumptions. We want to calculate the total number of units of time. We have that assumption, units of time. Yeah. So now we can do that. Yeah. All right. Yeah. So that's the, total units of time. Yeah. All right. So for the addition part, each addition corresponds to 1 unit, right? Each multiplication corresponds to 10 units, but 10 multiply 1/2, so we get a 5. So the total number of units of time expression is 5n squared plus 6n. Yeah. So that's our analysis answer. So in our first brute force method, that is our performance number. We find the answer, the total number of units of time. Okay? Yeah. All right. Then the next question, how to reduce this number. How to reduce this number. Okay? Yeah. All right. So now we need to work on the next question. How to reduce this number, improve. We want to get a better performance. How to improve this number. Okay, yeah. So the improvement strategy here. Yeah. Let's do an observation. In order to find some good improvement strategy, let's make some observation for a special property. Yeah. All right. So the observation is very simple. When we look at the cost ratio between two operations, multiplication and addition, that is the 10 to 1 ratio. So you can see the cost of multiplication much higher than the cost of addition. Okay, yeah. Based on that observation, so we have a conclusion based on that observation. So that is, for better improvement, we should focus on multiplications because there is more room to improve. More room to improve. The multiplication part is much larger than the addition part. So you have more room to reduce, to bring that number down. Okay, very natural conclusion. Yeah. All right, so we get this strategy. Okay, reduce the number of multiplications. Okay, so we set another strategy in order to solve this problem when we go to the next step. All right, so next, so let us apply the strategy execution, right? Yeah. I mentioned the execution factor in part 8.1. Here, how to reduce the number of multiplications. We need some special execution method. Yeah. Here, implement the strategy. Yeah. The strategy reduce the number of multiplications. Yeah. In the formula, total number of units formula. So we know the addition part much smaller than the multiplication part. Okay, yeah. So here, based on our analysis in the previous slide, we choose right strategy. So it tells us where to go, the direction to go. Yeah, we find the right direction. Work on the larger term. Focus on our investment on the larger term. Okay. Then execution. Now we need this one. How to get there. How to get there. So our next critical step, how to get there. We need to do a lot of work to get there. Okay? All right. Question, how to reduce the number of multiplications? Yeah. All right. So new question, another sub-problem we need to solve. Yeah, another sub-problem we need to solve. To solve this problem, we need strategy. Each step, we need strategy. Okay? Here, we need to study a simpler case. Remember, we used this before. So here, another time using this strategy. Okay. In order to use this strategy, next, let me introduce a commonly used method in our problem solving. So that is when we do experiments on relatively simpler cases. Here, n equals 2 first. N equals 2, let us write P2 first. P2 of x. A0 plus A1x plus A2 x squared. Okay, yeah. All right, so now let us try to make close observation here. So look at the last two terms. Can you see any special property here? Look at the a1x plus a2x squared. Can you find some special property between these two terms? They have a common factor x. Common factor x. That is the critical property we need. Critical property, common factor x. When we have a common factor x, then we can do something special here. All right, here, let me introduce another commonly used method in problem solving. Transform the problem. You change the form of the problem, but it is still equivalent to the original form, right? Equivalent. You make form change, but the value expression the same as before. But the look could be different. That's the transform, the problem. Here, we use this kind of transformation to change the structure for a new outcome. Yeah. So let me show you this idea. Transform the problem, this idea. Yeah. We do factorization. You know how to do factorization, right? Yeah, here. All right, the left-hand side, a1x plus a2x squared equals, we take the common factor x out. Okay, so we write x times parenthesis, inside the parenthesis, a1 plus a2x. Are they equivalent? Left-hand expression, right-hand expression, they are equivalent. They are the same. No change in function values, but the form, their forms are different, with different structures in their forms. That's what we need. All right, so now we want to take advantage of the form change. Yeah. Let us count the number of multiplications in two different forms. Yeah. For the left-hand side, 3. The first term, 1 multiplication. Second term, 2 multiplications. 1 plus 2, 3. Let us count the second expression, the number of multiplications. First multiplication, this red arrow, x times parenthesis, the whole parenthesis number. Yeah. But the second multiplication, a2 times x. Total, you only have 2 multiplications, right? Here, you can see the multiplication numbers, both sides, different. From 3 to 2, it is reduced by 1. How about that? How about this technique? Think about, how about this technique? Okay, yeah. Then let us summarize our analysis at this point. The conclusion is, when we apply the factorization technique, our gain is from 3 to 2. It is reduced by 1 from the original number. That's pretty good reduction. Pretty good reduction from this simple example. Okay. Then our next question. Can we generalize this idea to the general n? Because that 2 is n equals to 2 special. We want to see how this method works for the general n. That is the next thing we need to do. So in our video number 3, B.3, we need to, using this new method to solve our problem number 1. Let me stop here for video B.2.